Well, ladies and gentlemen, welcome. I'd like to welcome you first to the Smart Tooling presentation in mold sensors for liquid silicone injection molds. So as you see people walking by, just feel free to grab them and bring them out and into the audience. Now, some of you might think that we're here to sell molding services or tooling supplies or tooling, molding, molds for tooling, or sensors for the molds themselves, but no, that's not the case. We're here to do a presentation. But if you would like those services afterwards, please leave us your business cards and we'll be glad to contact you. I'm Chris Mitchell. I'm the Senior Project Engineer at Helix Medical in Baldwin Park. I'd like to introduce Vince Gallo, Applications Engineer with Priamus, and Troy Smith. He's the Vice President of Sales and Marketing for Remke Tools. This is where we're located. Helix Medical is in Baldwin Park. Remke is in Indiana, and Priamus is in Ohio. We've got some discussion points, and the way that I'd like to see this go is from the perspective of the molder with these applications, the perspective of the mold maker, and then the perspective of course, our sensor manufacturer. So the first three discussion points that we'll talk about are new tooling, existing tooling, maintenance, the different types of sensors, what data is monitored from the cavity itself, how the data is presented for interpretation. So our first presentation, our first topic is going to be on new tooling. Now, there's a lot of design considerations from the molder's perspective that we take into account. One, of course, is ease of operation. The customer's perspective, when it's molded, the impressions that the sensors leave, where it's going to be, what's going to happen to it in its post-assembly operations, etc. Now, from the mold maker's perspective, I'll turn it over to Troy.
Well, with the sensors, they have a certain size limitation to them. So we have to have a specific area in the cavity that we can put the sensors into. We're always trying to monitor the end of fill point. So we need, the smallest sensor right now on the market is a 1 millimeter sensor. So we need a 40 thousandths area to be able to locate the sensor. We also need to be able to run the wires through the mold and then get it out to where we can hook it up to the hardware to be able to interpret the data. So there's quite a few things that go on inside the mold to get a sensor into the cavity. And so we need to know that up front in the design phase so that we can accommodate the sensors in the cavity.
Troy hit it right on the head. With new tooling and putting sensors into the tool, it's important to understand what you want to do with that application and understand where your important points are inside those cavities. So it's good for us to sit down with the tool maker and with the molder and understand what we all want to achieve and the best way to get those sensors from inside the cavity. Keep in mind they're flush mounted inside the cavity, so they're actually seeing material. So we're going from inside the cavity to somewhere on the outside of the cavity and make that as easy as possible.
And the question comes into mind, are we cavity size limited? Well, we do have large cavities. We also have very small cavities. The real question is what we're going to do when, in fact, we want it or when we get it into the tool. Quite frankly, as far as the smallest sensor, I think we can talk about how to place those in the tool, where to place them, and specifically those sizes.
Again, right now, commercially available, the smallest sensor is going to be a 1 millimeter sensor. And so we need a place within that cavity to place that 1 millimeter sensor. Unless we want to do it outside the cavity on very small parts, we can make that the last point of fill and we can monitor it that way as well. But if we want to do it in the cavity, we need that space available to us.
I just need to make one correction. Priamus now has actually a smaller temperature sensor than 1 millimeter. It's actually 0.6 millimeter. You want to be very small with temperature sensors so they're able to react as quickly as possible when that material is seen. I didn't give Troy that piece of information yet, but now he knows.
Morton Thiokol didn't either. Existing tooling. With respect to can we retrofit tooling, we can and we will. But again, the consideration comes into mind, what is it we're trying to do to make the process better? In-mold sensors, whether they're temperature or whether they're pressure, are designed for a specific reason. And when we're able to monitor what's taking place in the cavities with the silicone, we are able to do a better job of processing, reducing scrap, reducing pressures, and we'll get into a little bit more with regards to the temperatures. But yes, we can retrofit it, but what's involved with that from our perspective is, again, where are the wires going to come out that are routed? What type of interface do we have to have for the machine? What kind of interface do we have to have within the EDAC system or with the RJG system, EDART? And I do want to bring that up. We are not, and I apologize, Vince, again, we're not specific to our in-house sensors. So from a tool perspective, if we have an existing tool, Troy?
Most generally, we can retrofit a tool for sensors in the cavity, but it may not be the exact fit since it's already been designed, and we may not be able to put it in the most advantageous location, and we may not be able to get the wires ran out through, but in most cases, we can put sensors in existing tooling. Again, we just have to look at the design and where we want to put them and stuff like that to be able to determine the best path for the wires and that sort of thing.
Can you all hear us? Are we loud enough? Wow, he's speechless. In briefly, what does it entail? Again, we're looking at a serious design change consideration for the tool. We're also looking at customer involvement. Very important to have the customer's approval, obviously, if it's not your own tool. Customers generally don't mind it when we ask them if we can improve things within the tool or improve things within the process. But it does come at a cost. It comes at a downtime, lead times, it comes with testing, and it comes with ensuring that that process is going to be robust enough. They're speechless. Maintenance considerations. Okay, what kind of maintenance is there in silicone tooling sensors? Well, when we get into the different types of sensors, you'll see a little bit of what's involved with regards to maintenance, whether there's seals or whether they're not, there's sleeves or other things that are involved with that. Typically, and I say this typically, our maintenance on these sensors while they're in the mold during processing is very limited. I think probably the largest maintenance area isn't even in real maintenance, it's in training. And I think that's one area where we can talk about at the end. So as far as from the molding perspective, very little maintenance with regards to while processing.
In molding, that would be correct, but the molder has to maintain the tools. And that's where you have to be careful when you're doing your PMs and that sort of thing. While the sensors and stuff are very capable of monitoring things within the cavity, you need to be aware of where the wires are at. You need to be aware of what dry ice could do to the sensor, which it shouldn't really harm the sensor. And you have to be careful with solvents. You don't want the solvents to get in behind the sensor where it can affect the wiring or the performance of the sensor. So when doing your PMs on your tooling, you need to have an effective mold maker or a tooling guy on that to be able to handle them appropriately.
These guys are taking all the good answers, but it all goes back to the slides previously. In the design phase, when you're figuring out where you want to put these sensors and how you get them to the outside of the tool. The ideal situation is you should never really have to remove these sensors. All you have to do is clean your mold. The sensors have O-rings on them. As Troy pointed out, if something gets past the sensor and affects the wire, then you can have an issue. There's caps for the outside of the tool, and they're basically just press fitted inside the tool, so no liquid, no material should be getting by any of those sensors.
Like I said, with regards to processing, there is very little maintenance within the tool. Now, going to what we do when we're in our regular PM cycle, this is very difficult, but the benefits outweigh that difficulty. From the moment you shut that tool off and you start taking it out of the press, you have to be mindful, and your techs have to be mindful of the sensitive wires that do come out for or going to the EDAC system or the eDART system. Now, from that perspective, when you get it to the tool room, wires are routed through different channels. They're not very complicated channels, but then again, as you take the tool apart, those have to be considered. And yes, as far as solvents and handling go within the maintenance department, there has to be a consideration for this. The wires are the most sensitive part. The sensors are robust, so we have to be cautious. Now again, training your tool room, training with regards to not just how they're laid out, but how the sensors operate. They need to know just as much as the processors do. It's very critical. Okay, types of sensors. I'll skip through both the fact that we have temperature and pressure, and to say that it is application specific for the selection of sensors. And I guess we can stop there, and I guess what do we mean by that? If we're looking at a pressure sensor and we want to look at what's in the cavity, you know that we're going to be able to see the pressure curves that take place in that cavity. How does that benefit us? Well, in reducing the amount of injection pressure that you need, or reducing the amount of hold times, cure times that you need, it's absolutely wonderful. And it tells us that data. Temperature sensors, haven't really found much use for temperature sensors within a silicone application, but we are silicone. Hopefully, raise your hand. Are you silicone molders or silicone related? Anybody? Going once? Okay, couple. You know that the silicones do have very sensitive curing temperatures. We could capture that. We could get actual data, and that's what we'll talk about with these two sensors. Actual data is going to be better, but you're not going to be able to do much with adjustments with silicone tooling because of the way that they're heated. Okay, types of sensors. I'm getting very smart at these, but I do want to let Vince tell you, and I've got a great green laser pointer. If you push there, you can point to those lasers up, or the sensors. So here's Vince.
This is just a quick illustration showing you two different types of sensors and two different ways of mounting them. So what you're looking at here on the far left is one of our 1 millimeter temperature sensors backed with a mounting nut, and then that same sensor backed with a distance sleeve, so you would have a plate behind here to support that temperature sensor. These distance sleeves are 40 millimeters. They can be cut to length, so you keep that sensor held in place very secure. And then the same goes with these pressure sensors. These are about 4 millimeter in diameter. Again, mounting nut and distance sleeve. Two options. A very good way of securing those sensors so there's no movement, of course. You don't want any movement. And there's also other types of dimensions and sizes, but this is the general way of how you would secure these types of temperature sensors inside your tools.
And when we back up to a couple slides ago when we were talking about considerations for retrofitting, well, you can see that you're going to cut through steel. You're going to go into cavities. When you talk about existing tooling, when you talk about new tooling, you can design those considerations into it. Okay, the type of data, why do we always say that, type of data? The type of data that's monitored from the cavity. We have the first one, which is actual cavity pressure and temperature monitoring. Again, we talked a little bit about it a minute ago, the value of having or seeing what those pressure curves are within a specific cavity. Very critical, very important to reduce or to, I will say, use better scientific principles in the molding process for better part quality at the end. We'll talk cure in a second. Anything to add with data?
It's important to understand what you're getting out of each curve. With a pressure curve, obviously you're going to understand how that part is curing inside each cavity. So if you have a 4-cavity tool, maybe you have a pressure sensor in each cavity, you can compare maximum pressures so that they're all equal prior to ejection, and you could set limits on those as well. Cavity temperature is very important, actually. It initially, prior to the material arriving at that temperature sensor, it just lets you know what your mold steel temperature is. So you can compare temperature values across the mold gradient and see if those are equal as well, because that also plays into shrinkage. So that's also important to consider. Now, once that material arrives at a temperature sensor, you know exactly where the material is inside each cavity. Now, I keep talking about multi-cavity tools, but the same goes with one large tool, maybe 5 foot long. You might have 5 sensors across that tool. It's letting you know where the material is inside each cavity. Instead of just going off of time-based valve gates opening, you know exactly where the material is. So it is important to use both temperature and pressure sensors inside of your tools.
Now, with implantable grade silicones, I've seen cycle times that have been as long as 360 seconds, where you start it up completely cold and you work its way up into a cured state and then cool it back down again. I can't tell you how critical it would have been at the time to have temperature settings or temperature readouts with a process in that case, covering platinum wires for overmolds. Very sensitive, very temperature sensitive. Why reduce cycle time? Well, it's important. If you know that you're curing a temperature and you're raising the temperature so that you can cure, it's extremely important to know when you get there. I don't think there's anybody here that hasn't stuck a thermometer inside of a turkey to see how quickly or how hot that turkey is. You can't tell by looking at the outside. You can't depend on that oven, can you? Well, stick this sensor inside and you're going to know when that cavity is up to that temperature. Okay, how data is presented for interpretation. Well, this is a very complicated, very technical issue, but to be quite honest, the very simple explanation is it is a combination of embedded software. There is external software as well as configured hardware. When we are using a system to record data, we have a dedicated hardware system that we would use for that. Not very extravagant, it doesn't have to be elaborate, but there is a dedicated computer system. I know that we could go extremely, and there are industries that use them with touchscreens and with other sophisticated, extremely sophisticated hardware. But in our case, a simple laptop or piece, or just a standard PC works extremely well. That, in a nutshell, for us. But it does get a lot more technical.
Sensors are very important inside the tool, but that's just one key piece of it. You also have to have the electronics on the other side. So you have your hardware and you have your software. Temperature sensors, pressure sensors usually react in about 2 milliseconds up to 10 milliseconds. That little bit of time is also very important. Then you need to communicate with the electronics. Now, in our case, our electronics reacts and communicates in about 20,000 hertz per second. Our software then also has to be able to display that information so the user is able to understand it and put it to good use. In our case, software reacts in about 250 hertz per second, creates smooth curves, understands where material is and what to do with it.
And with all that data, then, what you're creating with sensors in the cavities is a closed-loop system. You now have the press talking to the cold deck manifold. You have the cold deck manifold talking to the pumping unit. So everything is talking to each other to give you the most solid process for running your parts. Also to be able to run defect-free. So all this data that is being collected is very useful in how the machine operates and how everything talks to each other. So you naturally created a closed-loop system then at that point. Excellent.
Okay, well, just a couple closing comments. We talked briefly about training, and you can't emphasize that enough. With specifically Priamus, there's no shortage of good training available to us. We've taken advantage of that. With regards to our tooling and what we do and how we're able to train our folks with regards to what takes place in a tool, our tool makers are there for us, specifically Remke. We are going to be available afterwards. I want to give an opportunity for the folks to give a closing comment. But please don't, there are no questions about specific applications, but if you do have something that you'd like to look at, we'll be glad to answer those questions. Again, it's not a cheap sales talk, but we are here for that. Again, I'm Chris Mitchell with Helix Medical, and this is
Troy Smith from Remke Manufacturing. As being a mold maker, again, not a sales pitch, but if you do have projects you'd like to discuss or whatever, I can give you my contact information, and we can go from there then. Thanks.
Vince Gallo with Primus System Technologies. Thank you very much for your time. Have a good rest of the show.